Hi everybody. I thought it would do something with the strategy design pattern. The strategy design pattern is interesting because it enables us to use a wide variety of algorithms. And one of the things I wanted to try and do was to come up with an algorithm for numerical integration. And one of the things we happen to know about numerical integration is it can work on a wide variety of functions with a wide variety of algorithms. So let's create a new Java class. And in this new Java class, we'll call it numerical integration. And in our new numerical integration class, maybe we should make it an interface. Let's make it an interface so that we can implement it with multiple algorithms. We'll have a numerical integration strategy pattern. Well, a numerical integration interface uses the strategy pattern, so I'll just say SP for strategy pattern. Okay. Now, when we want to do numerical integration, if we want to make it very general, we'll want to create a few different elements that we have to implement. There are a couple of things we need to know about numerical integration. One thing is we have to have a point at which to start, a point at which to stop. We need some, we'll call them limits to the integration. We're also going to need a number of partitions. We don't quite know what kind of integration we're going to do. It could be Simpson's rule or trapezoidal rule or rhomboids or whatever we're using, Monte Carlo, all kinds of fancy things for integration. But one thing we do know is that we're going to have some kind of a function. And it'll be a general function. We don't know what kind of function. We don't know how complicated it'll be to evaluate. What we don't know about the function is just about everything except for one thing. It has to have a single input and a single output. So we're going to do one-dimensional integration. We do that as a first example because it's very important to make the first example as simple as possible, but no simpler. So let's see if we can do some prepared typing here. Some prepared typing. I've got this thing called set function, which obviously gives us some kind of function that can act as a parameter. Set the number of partitions, that sounds good. Set the limits of integration because we need a beginning and an end. And there's another thing we might like to set, probably the tolerance. So let's try and do that as well. We'll do a simple set, we'll call it tolerance. And if we can sort of use that tolerance to try and define part of the limitation for the integration, that would be very helpful for us. And so we'll make that a double, and we'll call it the tolerance. And I think that's probably all we're going to need for a one-dimensional integration system. This is a function that's being used as a parameter. Let's examine this function. Let's see how general it is and what we can do with functions that are implementing this thing, whatever this is. And so we take a look and we say, aha, function is an interface and it evaluates a double and returns a double. This is the most general way I could think of to create a real valued function. Real value. Could have done this with complex numbers, but I think it's better if we don't. So we've got, let's see now, some sort of numerical integration strategy pattern. The power of the strategy pattern is that it enables us to manufacture instances of algorithms which can operate on this wide variety of different functions. And so what we'd like to do is we'd like to try and implement the numerical integration strategy pattern. And if we would like to, I don't know, maybe not put too fine a point on it, we could probably just call it, I don't know, the numerical integration interface. Just so that we all know that it's a interface. Now it turns red in my browser because it doesn't match the name of the file, but what I can do is I can rename the file to call it numerical integration interface. So when I go to define some sort of a class which implements the numerical integration interface, I have to provide implementations for each one of these methods or declare the class as abstract. So class, let's call it trapezoidal. Trapezoidal, trapezoidal. And let's see, implements the numerical integration interface. Well, that's not too bad. But now I'm getting all this red, and the reason I'm getting the red, it's not abstract, so we have to provide implementation for all the methods. And so here are all the methods in here. We're not going to insert the overrides because that just clutters up the joint. And here are all the functions. So there's got to be somebody who can set a function. And what we'll do here is we'll provide a function f, and that'll be private. And now we'll have a limit of integration, start and stop. It looks like we're going to need to have doubles for that, so we'll just say double. Let's see. And for our start and stop, we'll have to do the similar thing. This dot start equals start, and this dot stop equals stop. And so now we've got a basic implementation for the interface, but the one thing that we seem to be missing from our numerical integration that I think everything needs to do is the command to actually start to integrate. And the integration should probably return some sort of a value. So we'll say something like this: public double integrate. And that causes an error. And the error says, well, you didn't provide an implementation for the integrate method, which is really the heart of our algorithm. So now the big question is, well, how do you do integration with trapezoidal methods? Well, let's see now. I happen to have a method already implemented here, which I can copy into the screen so that you can see it. And this will do trapezoidal integration. And I think we can just paste it right in here. And that seems to work reasonably well, except for the max iterations, which we have over in here. And we can see, aha, max iterations. That should probably be what we're using for n, right? Set number of partitions, max iterations. So we'll use n for that. Or we can make it a global. Let's see. Shall max iterations be something that we use as a parameter? This is a big question in my mind. Now, is it part of the general numerical integration interface, or is it one of those parameters that we just set? This becomes one of those strategy issues that you kind of have to decide on. If max iterations has something to do with the number of partitions, Maybe that's a different thing. Let's see. Max iterations controls the behavior of my system. I have a feeling we better make max iterations something that we can set. So let's do that. Set max iterations. Make that an int. Call it max iterations. And then what we'll do is we'll make this a double. I think I can paste it in, but I'm not sure. Let's try. Paste. Whoops. Max iterations. Equals, I don't know, make up a number, 15 by default. And this will have to be an integer. Oh, and it needs an underbar. And now we see, aha, we have to have a new method for setting the max iterations. And what we'll do here is we'll say max iterations equals max iterations, and that should give us a method for doing our integration. And so you have it. So now we've got basic interface. We have a trapezoidal implementation, and now the next time we want to do an implementation of the numerical integration interface, we can subclass the trapezoidal class, and then all we have to do is override the integrate method. And that can be of great use to us. So one of the things that might make sense for us to do is to have a family of different algorithms for implementing the numerical integration interface, set them one at a time, and then compare them against one another for the same given parameters, number of iterations, the n, the tolerance, the start, and the stop. And we can even use the same function. And that is a great example on how to use strategy design patterns. For the strategy, we can change the algorithm at will using an entire family of one-dimensional functions, and then compare our integrations against one another. And so now we've got a good example for the strategy design pattern.